All right, in this video, we're going to talk about infinite geometric series. It's the first time in this class we've really talked about infinity in any sort of serious way. And you know what? Next year in calculus, we're going to talk about infinity all the time because we're going to talk about limits, specifically as x goes to infinity. That's going to be really, really common. But for now, we're going to think about n going to infinity. We're going to think about having an infinite number of terms. So let's start with something that is obviously going to diverge. Let's take the series that is 2 plus 10. Sorry for pausing. I was like, do I want to keep the comma there or just write it out? 2 plus 10. Oh no, I keep accidentally hitting a button. 2 plus 10, this is my common thing. It's like regular class. 2 plus 10 plus 50 plus 250 plus 1,250. Yeah, you guys should check me there. Plus ... forever. Now, I hope we could all look at this and think, there is no number that this is equal to. This is impossible, Sean. You can't do this. And so that's right. And we're going to say this diverges because it goes to infinity. Right? It's getting bigger and bigger and bigger and bigger, and it's never going to settle on one specific number. Whatever big number you want, you can just add another term. Oh, it's bigger. We did it. And so there is no stopping point. It goes forever. It diverges. That is the fancy term. And you'll get a whole lot of things to prove this rigorously. We're not doing that. You can just use your intuition here. It seems obvious. Now, what we want to look at is a situation where maybe it actually does converge. So we're going to specifically look at situations where the absolute value of r is less than 1, which is a fancy way of saying that r is in between -1 and 1. It's sort of a proper decimal or a proper fraction. It is something less than 1 or greater than -1. It's a fraction in between -1 and 1, and it's a proper fraction. Okay, so we remember, hopefully, from our previous formula that Sn was equal to A1 multiplied by, I didn't quite write it like that. I wrote 1 minus r to the n over 1 minus r. So keep that in mind. We're going to get back to this in a second. And let's think of the situation like the following. Let's take the situation 4 plus 2 plus 1 plus 1/2 plus 1/4 plus 1/8 plus ... forever. It is always getting bigger, right? You add another term and it does get bigger, but it's getting bigger by a smaller and smaller and smaller and smaller amount. And so in this one, our A1 is equal to 4. Our R is equal to 1/2, right? Each term is 1/2 of the term before it. And here we want n to go to infinity. We want n to get as big as you want. And so when you're typing this into a calculator, which is mostly just going to be Google, since Google can handle a lot, you're going to just type in 1 billion, type in 1 trillion, huge numbers, okay? Whatever number you want, bigger. Okay, so let's think about this. Our Sn is going to be equal to 4 multiplied by 1 minus, this is 1/2, and it is important to have this 1/2 in parentheses, to the n, all divided by 1 minus 1/2. And what I really want to talk about is what's happening right in here. Okay, so we obviously can't type infinity into a calculator, but what if we type in 1 million? What is 1/2 to the 1/millionth power? So if you do this in Google, if you do 0.5 to the 1 million, it's just going to tell you 0. Now, is it exactly 0? No, it's not. But it's so infinitesimally close, it's so stinking close to 0 that it might as well be 0. because it's 1/2 of 1/2 of 1/2 of 1/2 of 1/2 of 1/2 a million times, right? You got to keep doing that a million times. I would never finish saying it. I would dehydrate myself trying to say it before I could actually do it. It's so tiny, right? Because after only 3 times, you're all the way down to 1/8, right? 1/2 of 1/2 of 1/2 is an eighth. That's pretty small. Another half, it's a 16th. It gets really, really, really tiny. And so what we want to think about is that this expression, as n goes to infinity, just becomes 4 times 1 minus 0 over 1 minus 1/2 as n goes to infinity. So this idea of as one thing is going to infinity is going to be really common next year. And any fraction to a power, we're going to get to it in a second, even if it's like 0.999, if you have a high enough power there, it is going to eventually get really, really close to 0. And so, well, 4 times 1 minus 0 divided by 1 minus 1/2, that's really easy. That's just 4 times 1 over 1/2. 4 divided by 1/2 is just 8. Okay. I want to think about this in a couple of different ways. I want you to, with your own calculator, take a ratio that's really close to 1. Let's get a ratio like 0.99. That's so close to 1. But let's take it to the 1 millionth power and see what happens. So I'm going to do this with my calculator as I talk it out. So 0.99 to the 1 millionth power. Wow. Even that, it's only a million. Million's certainly a lot less than the highest number you could think of. Even this, according to Google, is just going to go to 0. Now, again, I'm going to emphasize that is an estimate. It is not literally equal to 0, but it is so close to 0 that the distinction is irrelevant. The distinction is sort of like almost meaningless. And so we get this point, even something really close to 1. It doesn't matter what fraction you have, as long as this value inside here is in between -1 and 1, exclusive. You take it to a high enough power and it's going to go to 0. So this is going to inspire in us the general formula. So we know that Sn, just reiterating what we had from before, is a1 times 1 minus r to the n divided by 1 minus r. If the absolute value of r is less than 1, then as n goes to infinity, which again, I know it's spooky, but it just means as n gets really big, Sn is going to approach a1 times 1 minus 0. Because as n goes to infinity, r to the n is going to 0. So this thing that I have up here, this r to the n, is becoming this thing in this situation. And then divided by 1 minus r. Obviously, 1 minus 0 is just 1, and if I'm writing times 1, I don't have to do that. So we say Sn is equal to, actually we just say S is equal to a1 over 1 minus r, again, if the absolute value of r is less than 1. And what these are meaning, S is the infinite series, which actually is a bit redundant. Series means infinite series. You have to say partial if you only mean partial, but I'm going to write it in there. The infinite series, adding these all up and up and up forever, is just equal to this first term divided by 1 minus the common ratio if the absolute value of r is less than 1. I'm going to keep emphasizing that because I don't want you using this formula for common ratios of 2. Doesn't work then. Has to be a common ratio of something that is small in between -1 and 1. All right, we'll do a couple of examples and then come back, or that'll be the next video. Okay.